much for the introduction, and thank you all for coming today. So yes, today I will present basically my dissertation work I recently defended in September, and now I'm an MPP at Goddard working with Nikki Weil. So the bigger picture of this work is really to gain more understanding on how the solar wind is formed. So how we do that is we develop a methodology that uses the ADAPT-WSA model to identify specific source regions of the observed solar wind and investigate how populations of wind from the same source are released or accelerated. So WSA is well known in the community as an operational model. However, recent advancements, including the pairing with the DAT maps, have allowed us to refine a more robust methodology for research. So I'll discuss that and some of the new capabilities that we've developed, over the past few years that I've been involved in this work. So I'm just going to start with one slide on the corona, and then I'll have some discussion on the solar wind that really motivates all the different studies I'm going to talk about today. So pertinent to this work are two types of streamers that form in the corona. So you have helmet streamers and pseudostreamers. Helmet streamers are dipolar, and that they form between two coronal holes of opposite polarity. They tend to be larger. The underlying closed field undergoes more expansion. On the contrary, pseudostreamers are unipolar, so they form between two coronal holes of the same polarity. And you can see in this eclipse image that this pseudostreamer is much smaller than the surrounding helmet streamers. And typically this happens because their cusps converge lower down. You can see in the differences of the cartoon. And it kind of prevents that underlying closed field from expanding. So onto the solar wind, which is essentially the boiling off of the corona in this continuous outward flow of plasma supersonically away from the sun. So traditionally, the solar wind is described based on its observed speed at 1 AU and separated into two populations of either fast or slow. This is a well-known plot of observed speed at Ulysses as a function of heliographic latitude. These data are overlain onto remote coronal observations from the same time period. And so a critical component of my work is identifying the source of the solar wind back at the sun. And one of the ways that this is done is, this plot is an example of one of the ways this is done in like a very general sense. So what this kind of shows is that the fast wind can be seen from emerging from continuously open field lines that form coronal holes, while the slow wind is emerging from the streamer belt. So this study and others have really kind of shaped how we think about the solar wind, in which origin and speed are inextricably linked, meaning they really can't be separated, or at least that's how we talk about it. So other solar wind properties, such as the 07 to 06 charge state ratio and the ratio of iron to oxygen composition, have also been shown to be inversely correlated with solar wind speed, thus supporting this traditional paradigm. However, this has only been shown over global spatial scales or longer time scales. So both of these quantities I just mentioned are conserved, which means they're set in the corona and they remain unchanged as the solar wind propagates. And the iron to oxygen ratio in particular is set lower down in the corona, and it's used to gauge if the plasma has more elements that are easily ionized. So when this ratio is large, the plasma is said to be FIP enhanced, with FIP referring to the first ionization potential. So the same enhancement is also observed in remote observations of the closed field corona. So this is another way which we can link what we're observing in the solar wind to what's where it's coming from on the sun. So initially, theories pertaining to solar wind acceleration attempted to self-consistently account for both fast and slow wind. This has resulted in two leading but different physics-based models. The first being wave turbulent driven, in which you have fluctuations at the surface that produce wave pressure gradients that accelerate the solar wind. So in this model, the slow wind is emerging from flux tubes that have undergone more non-radial expansion, which is what you see at the boundaries of coronal holes. This expansion is typically quantified by the magnetic expansion factor, which I'll discuss in more detail later on. But a key point in this theory is that these processes are only describe plasma along open field lines. In the second theory, acceleration is driven by magnetic reconnection, in which the closed field opens up by reconnecting with the open field and injecting energy into the solar wind. So initially, these two theories were, in a way, competing because they each were trying to account for, all the solar wind that were like both fast and slow populations. So over time, the solar wind has been viewed as these two populations. However, in the past decade, this simple view has been called into question because not all the solar wind that we observe can fit into this description, especially when you're looking at like smaller spatial scales and time scales. So just one example, the tops of helmet streamers have been observed to release plasma blobs that are released like with pinch-off reconnection, but then they're observed to still accelerate after the reconnection has occurred, suggesting that there's multiple acceleration mechanisms at play. There are also several other examples, but they've all led to both acceleration theories being further refined. So the original reconnection theory has been since supplanted by the separatrix web or S-web theory. And so what's interesting about this is that it pertains mostly to the origin and release of the slow FIP-enhanced wind, where like the closed field coronal wind, that's where it's coming from, versus trying to describe the acceleration of all solar wind, as in the original theory. So the S-web theory suggests that slow wind originates from closed field plasma that's released at the boundaries of coronal holes. I think you can see my laser pointer. So these coronal hole boundaries converge higher up in the corona, and they map to what are called S-web arcs. So you can think of it this way. Essentially, the heliospheric current sheet here is one giant S-web arc that's formed by helmet streamers, and the smaller arcs up to 30 degrees away are typically formed by pseudostreamers. And a key point of this theory is that it allows slow wind to be released far from the heliospheric current sheet, and we actually directly test this in my research. So in a recent review of solar wind physics, Weil and Borowski proposed a new framework to describe pathways that the solar wind can take from its source out into the heliosphere. There are a few fundamental differences between the old and the new framework. First, the source region is now defined by the specific magnetic topology in the lower solar atmosphere. So coronal hole, quiet sun, active region. In the old paradigm, the source was always described as open or closed field, or in a more general sense like coronal hole or streamer belt. Second, the release and acceleration mechanisms are considered as separate steps, which allow them to be governed by entirely different mechanisms if needed. They don't have to be different, but it still allows for that. And third, the observed speed isn't really discussed anywhere in this framework, where in the old paradigm it was a big part of our language and like almost a central defining factor. So from the same review, they synthesized 3 questions that pertain to solar wind formation. So where on the sun does the solar wind originate? How is it released? And how is it accelerated? And so the answer to the first question for a given set of observations can really only be determined through the use of a model. Like we discuss these other ways in which we talk about source and these other methods to relate what we see in the solar wind to what we observe in the corona. But if we're going to talk about source more specifically, we would need a model to be able to connect in situ observations back to their source. So in this research, we employ the ADAPT-WSA model. It's 2 models coupled together. Has some more rigorous capabilities that have come out recently, and it's well vetted. We develop a methodology to derive source regions of the in situ observed solar wind. We conduct 3 different studies that address the formation of either specific populations of wind or a specific set of observations. So the first study, we're looking at if field line expansion accelerates the solar wind that emerges from pseudostreamers. And in the second, we're looking at particular structures in the quiescent solar wind that are considered signatures of reconnection. And then each of these studies sort of led to significant model development and modifications, which enabled us to apply these techniques to the first observations of Parker Solar Probe. So when applicable, I'll discuss our results in the context of this new framework that I was just showing previously. So first, an overview of the models we are using. ADAPT is a model which produces photospheric field maps from magnetogram observations. Using ADAPT makes this approach more robust because ADAPT uses flux transport modeling to account for solar time-dependent phenomena. So we account for differential rotation, meridional flows. It also allows us to account for the lack of solar far side and polar magnetic field observations. ADAPT produces an ensemble of 12 solutions or realizations that represent statistical uncertainty in supergranulation and random flux emergence in the photosphere. And these maps are also synchronic, which means they represent one moment in time on the sun, which can only be achieved through flux transport modeling. So not all photospheric field maps really represent one moment in time. They're really more of a summary of what's going on over the whole rotation, which is 27 days. So each set of maps are then used as input into the Wang-Schily RG or WSA model, which actually couples two potential field type models to derive the coronal field. Using the two different models provides a more realistic magnetic topology of the upper corona compared to other approaches. So we can go out from anywhere between like 5 and 30 solar radii typically. Then we use an empirical velocity relationship to determine the speed at that outermost boundary of the model. And it's a function of both expansion factor and coronal hole boundary distance. So expansion factor is related in some way to the wave turbulent driven acceleration theories, as I mentioned previously. And the coronal hole boundary distance parameter can be used as a proxy to determine if a foot point is near or far from the open closed boundary. So it kind of can be used as a proxy for like the likelihood that reconnection is occurring. So that the model propagates individual solar wind parcels outward along field lines that are magnetically connected to spacecraft. And then it allows the parcel's time of arrival to be correlated with in situ observations. So this approach is more accurate than other methods which actually do the opposite, like they're mapping the observed solar wind backwards from the spacecraft to the sun, or we're propagating solar wind outward. So when you couple WSA with ADAPT, we have an ensemble of 12 realizations of the coronal field and the spacecraft connectivity to the surface for a given moment in time. And then we can choose the best realization by comparing the model output with observations. So not all modeling approaches actually compare with observations. And so if we perform poorly at a certain time period, then I wouldn't use that as part of my research, basically. So the first study is looking at field line expansion quantified by the magnetic expansion factor, and if that plays a physical role in the solar wind acceleration occurring at pseudostreamers. This expansion factor measures the rate at which an Earth-directed flux tube expands in cross-section compared to a purely radial 1/r² expansion. It was originally defined by Wang and Schily in 1990. In the literature, it's denoted typically by F sub S. And Wang and Schily demonstrated that expansion factor can be used to derive the observed speed based on these two quantities being inversely related. So you can see that here in this cartoon of a helmet streamer where you have fast wind emerging from the centers of coronal holes from nearly radial open field lines, small expansion factors. Then you have slow wind emerging at the boundaries with large expansion factors. So this inverse relationship between speed and expansion factor has been challenged in recent studies concerning pseudostreamers, because at the pseudostreamer cusp, those open field lines are the same polarity, so they typically converge lower down, like I was describing previously, and resulting in like lower expansion factors. So a few of these studies identified just a couple cases where pseudostreamer wind is observed to be slow, where the original Wang-Schily relationship would predict fast wind would come from here because the expansion factor is so small. So this is another one of those scenarios that can't really be described by the traditional sort of two-state solar wind paradigm based on speed. So yes, the purpose of this study, as I've said before, but we set out to do this in a more comprehensive way, so not just identifying a couple cases. So we wanted to identify a large sampling of periods where multiple spacecraft at L1 observe pseudostreamer solar wind, and then try and perform a statistical analysis to test the original Wang-Schily relationship. So this is just highlighting the methodology to identify the specific field lines that are forming pseudostreamers. So even though this methodology is applied to pseudostreamers in this work, it can be used to identify the source of, the solar wind sources for like any source region. It doesn't have to just be pseudostreamers. And I use this throughout the other studies I'll present today. So first we just began looking through WSA output over like a decade to identify pseudostreamers. And this is just an example of one period. It's July to August 2014. And on the left is standard WSA output, which I'll continue to show throughout this talk. So the top panel is the model-derived coronal holes, and those are the open field regions and the sources of sort of all the solar wind outflow. And the model-derived solar wind speeds in color scale, and the background gray scale is the polarity at the photosphere. And then you have the middle panel, which is the ADAPT photospheric field, the input map that drove the model solution. And the bottom panel is the WSA-derived coronal field at 5 solar radii, and you have the heliospheric current sheet, of course. So just to zoom in on this top plot. So these white crosshairs are actually mark we call them the subsatellite points. They mark the heliographic location and time of the spacecraft. So in this case, we're talking about stereo A. Basically, and then the black lines connect basically stereo A to the to 1 solar radii. So the black lines kind of represent where was stereo A observing the solar wind. So they're the sources of the solar wind observations. So here's an example in green of potential pseudostreamer. We have 2 coronal holes that are near each other. They're both in the light gray, so they're both outward polarity. And these dates correspond to when the solar wind would have left the sun as opposed to when it would have arrived at the spacecraft 3 to 5 days later. So in this case, solar wind is emerging from the sun on July 12th, if they're the pseudostreamer. Oops, sorry. Okay, so then the next step is to determine if any of the 12 ADAPT-WSA realizations accurately derive the observed IMF and solar wind speed for 3 to 5 days from July 12th. And so since we're using ADAPT maps, they represent one moment in time. So we don't expect good agreement throughout an entire rotation. We're only looking at the few days that we ran the model solution for. So in this case, we're looking at this region here. And for that few days, the model is performing well. So this is a clean case to look at, basically. So I'll revisit this plot in a minute, actually. So then we use the 3D visualization software to plot the WSA-derived coronal magnetic field for the chosen realization. And this helps to confirm that we're actually looking at a pseudostreamer. So in these figures, we're only plotting the field lines that connect to stereo A. So you can think of these field lines on the right in color as the exact same as what you're seeing in the black in the 2D plot on the left. And WSA retains all the information for individual solar wind parcels that are like essentially launched out of these field lines, and it tracks like when those parcels would arrive at the spacecraft. So we're actually able to obtain the time of arrival of those parcels and look at the in situ data in that way. So highlighted in green here on the left is the 2 model-derived solar wind parcels in blue that left these 2 field lines in green. So for each pseudostreamer, we're actually looking at the last 2 open field lines associated with the pseudostreamer. And then we compare the expansion factor of those field lines with the observed speed. So we repeat this methodology for each region of interest, and we identify 38 periods in which either stereo A or stereo B observed pseudostreamer wind. So before I discuss the results, one thing we found throughout the study was that the magnetic topology of a pseudostreamer can vary from one side of the cusp to the other. So this is the same pseudostreamer we've been looking at, and if you look, one side is grounded in a strong active region of about 195 Gauss, while the other side is grounded in weak field that's about 10 Gauss. So the magnetic field at the foot points of these field lines greatly affect the expansion, you can see in this table, and it creates this sort of asymmetric dome when you're looking at the cross-section of this pseudostreamer, essentially. So instead of averaging over the entire pseudostreamer, we plot the solar wind speed versus expansion factor for just the individual field lines. So here is one plot of our results. We're looking at solar wind speed versus expansion factor for 38 pseudostreamers or 76 individual field lines that form the cusps. And the various spacecraft observations are indicated by the different shapes. Solar wind speed observations are averaged over plus or minus half a day from the model determined arrival time of the parcel. And so those error bars represent the standard deviation in solar wind speed over like a one-day bin. The photospheric field strength at the foot point of each field line is in color scale. And so the first thing that we can immediately gather is that the observed solar wind for these pseudostreamers is all slow, less than 500 kilometers per second. So this is consistent with prior work, which identified 1 or 2 pseudostreamers with slow wind observed at spacecraft. So since the wind is slow, we expect higher expansion factors for all these pseudostreamers. So we then calculate the Pearson correlation coefficient, which reveals that there's a statistical relationship between 2 variables, and the p-value, which determines the probability that a correlation could have occurred by chance. So we expect the p-value to be 5% or less when converted to a percent for a statistically significant correlation. So if these 2 variables were inversely related, this would be less than 5%, and this would be at least moderately negative, so like minus 0.5 to minus 0.1. So there's really no correlation for these data points. However, since the magnetic topology can vary from one side of a pseudostreamer to the other, we decided to separate field lines out by their source region at the photosphere. So here are only those field lines, or only those pseudostreamers that have quiet sun magnetic field on either side of the cusp. And so when we look at just these pseudostreamers, we see that several field lines can have the same expansion factor, yet the solar wind varies over the entire range of speed exhibited in the study. And again, no correlation. And it's not even negative, and the p-value is far too high to have statistical significance. So these are the remaining field lines. So here are pseudostreamers with at least 1 active region on either side of the cusp. So this is the only population where we see a correlation coefficient that's right on the edge of negligible and low, but still not that moderate or high correlation that we were looking for. So lastly, for all the field lines in this study, we plotted the observed speed against the distance that each field line is from the model-derived open-closed boundary, or you can think of it as like the model-derived coronal hole boundary. So the value between 0 and 2 indicates that you are close to the boundary, where reconnection is likely, and anything higher than 2 means that we are deeper inside a coronal hole, like in that continuously open field region. So what's interesting here is that we at least derive the expected correlation for these 2 parameters, even though it's only a moderate correlation. So also, only the slowest speed emerges from field lines closer to the boundary, where the field lines are constantly opening and closing. And then as you move farther from the boundary, a wider range of speed is exhibited, since there's a mixing of continuously open and closed flux tubes. A mixing between continuously open field and those field lines that are only open intermittently. So yes, and just in conclusion, in this study, we identify 38 periods where we have 3 different spacecraft observing pseudostreamer solar wind. This is the largest sampling of in situ observed pseudostreamers identified to date. The primary conclusions is that all of the observed solar wind for these pseudostreamers is slow. It's significant in and of itself because this has never been thoroughly investigated. Second, in all instances of testing the inverse relationship between expansion factor and speed, at least for pseudostreamers, there's not a statistically significant negative correlation between these variables. So this is kind of expected because we're really only looking at open-closed boundary field lines where the field's constantly opening and closing. So we would expect a stronger relationship between expansion factor and speed if we were really deep inside a coronal hole with even larger coronal hole boundary distances that we saw in the previous plot. So we want to test this in future work. So lastly, it was interesting to find those pseudostreamers that have asymmetric cusps due to one side having an active region and the other side just being planted in quiet sun. So this is not unexpected, but identifying an observed pseudostreamer with this topology really kind of points to the necessity for this framework, where we have to consider the local source of the plasma and not just the large-scale magnetic structure such as pseudostreamer or helmet streamer. Active region plasma, stronger magnetic fields, higher temperatures, and so it's not a surprise that maybe the solar wind observed from those regions will be different. So the second study was focused on determining the source regions of periodic fluctuations in solar wind density structures, known as periodic or quasi-periodic density structures. So they've been previously identified at 1 AU. They have characteristic frequencies between 80 and 120 minutes. So what's interesting is that they're typically observed with corresponding changes in composition and charge state, but not a change in solar wind speed. So thus, without that change in speed, they cannot be produced via flux tube expansion, and they're likely formed by reconnection back at the sun. So these PDSs drive oscillations in the magnetosphere at the exact same frequencies. And that's what these data are showing here, is solar wind density enhancements at wind that are lasting approximately 90 minutes, and the same enhancement observed at GO 68 minutes later in the magnetosphere. So PDSs are important because they fill the quiescent solar wind, these periods when we don't observe large eruptive events like CMEs, and they make up a large component of the ground state of the solar wind. So these same structures have been observed in stereochronograph data, and so thus they are thought to form back at the sun via reconnection. So I was involved in a study which set out to determine if PDSs had been observed closer to the sun than 1 AU. So I used the ADAPT-WSA model and the same methodology as previously to determine the source regions of any structures that the co-authors might find. So my contribution was critical to test the S-web theory because we were looking to see if any of these structures were observed far from the heliospheric current sheet, providing evidence that reconnection can occur far from the heliospheric current sheet. So the timing of this study was also critical because we were working to publish before Parker Solar Probe data was available. And so the idea was to revisit Helios data from the 1970s because prior to the launch of Parker, Helios was the closest spacecraft to observe the solar wind from the sun. So this was kind of like a prediction paper in some way. So we employ the same techniques as I described before. However, there are several challenges unique to this study. Helios data is extremely old and at times poorly documented. There's a lot of data dropouts. And also the model was not capable of deriving the source regions for Helios observations until this study. So it was a very manual process. This is just a glimpse of what that looked like, where we had to actually calculate the model grid cells by hand and so forth, or with Excel. So the co-authors of this work identify 5 events in which trains of PDSs were observed between 0.3 and 0.6 AU. So I'm only going to show 2 of the events here, and I'm going to discuss only the data analysis to provide context, but really I was more the modeling side of things. So the first event is observed over 6 hours in C2 at 0.37 AU. So I'm not going to go over all these observations, but I'm just going to focus on a few. So we have proton number density here, magnitude of the magnetic field, temperature over here, and plasma beta in black here. And then the red is the entropy per proton. And entropy per proton is an interesting observation because it has been shown to empirically follow charge state measurements. So when that conserved quantity charge state is not available, this is a good tracer of that. We can look at that as well. So the average periodicities of these structures is 120 minutes. And that's what these red sector boundaries are marking, is local minima in density. And so, and embedded within that, they identified a 30-minute periodicity of embedded substructure. So what's interesting about these boundaries of local minima and densities, they also vary concomitantly with temperature and magnetic field and these other observations I was talking about. So, and what's also interesting is that if you look at this bottom plot here, these structures are pressure balanced. So that means that the total pressure in gray is not changing over the entire structure. And it indicates that these structures will maintain their periodicities even as the solar wind propagates outward. So for the same 6-hour event, essentially, these are the modeling results. So the trajectory of Helios is overplotted in red. And so the source regions are indicated by the red dots. These events map to, if you can see my laser pointer, the southern polar coronal hole boundary. And this is, if you look back at the photospheric fields in quiet sun. And for this time period, Helios is skimming the heliospheric current sheet. And if you look back at the coronal hole plot, there are no mid-latitude coronal holes present, so it's likely that this plasma is emerging from a large helmet streamer forming between the two polar coronal holes. So the second event, and the most interesting, was in June 1981 at about 0.38 U. The average periodicities are 6 hours and 128 minutes that they identified, and these are just the modeling results. So there's much more solar activity going on in this time period. And the source region of this event is a small mid-latitude coronal hole that maps to an active region. And what's interesting, as in the plot B, is that we map to up to 18 degrees away from the heliospheric current sheet. So these structures had not been previously identified as forming far from the current sheet. And then if you look back at plot C, the coronal holes are all, like the surrounding coronal holes are all like the same polarity. So this magnetic field configuration would be that of like a small pseudostreamer, which would create that S-web arc far from the heliospheric current sheet. So yeah, just in summary, myself and the co-authors identify for the first time in situ measurements of these quasi-periodic density structures embedded in the slow solar wind closer to the sun than 1 AU, which provides more confirmation that they're forming in the corona. The modeling aspect is necessary to test the S-web theory because we're able to look at the source of the solar wind and see if it was near or far from the current sheet. So we do identify both scenarios. And so this work also served as a test to see how WSA would perform for observation inside 1 AU. And kind of what was birthed out of this study was that now the model, all like Helios and these older magnetograms like Mount Wilson and Wilcox are like integrated into the model in a more streamlined way so that we can, readily do more studies like this. So we're definitely interested in collaborating with others that want to look at these older data sets as well. So in the final study, we apply the same techniques and modeling to derive the source regions of the new Parker Solar Probe data. So as mentioned previously, prior to this work, WSA was unable to derive the solar wind if it came from anywhere else, or if it was measured anywhere else than L1. So all of these studies sort of led to me developing and testing code to have the model be able to propagate the solar wind to spacecraft that vary in radial distances. So today I'll just discuss results from the first encounter. We modeled the observing period from October 30th to December 6, 2018. The spacecraft trajectory during this time period is shown in purple in this plot. This encounter occurred mainly on the far side of the sun as well, where we don't have magnetogram observations to drive models. So this is a movie of all 12 realizations of the model-derived global coronal field at 5 solar radii. You can see the model-derived current sheet in yellow varies only slightly from one realization to the other. So Parker's location mapped back to this boundary is marked with the red crosshairs and the dates corresponding above. So this visual best summarizes Parker's location relative to the heliospheric current sheet for most of the first encounter. So after we've mapped Parker back to this outer coronal boundary, we then calculate the minimum angular separation between Parker's location, or the red crosshairs, and the model-derived heliospheric current sheet in yellow. And that's what's shown here on the right. So this is also just one realization. So this is a new WSA data product where we actually can provide like a quantify the spacecraft distance from the heliospheric current sheet. This also came out of this research. So for the inbound leg of the first encounter, oh, sorry, I just wanted to mention too that time is like in reverse in both these plots, so it's a bit tricky to kind of follow along. So I'm going to try and step through it. So the inbound leg of the first encounter, Parker's skimming the heliospheric current sheet, separated between 0.5 and 5 degrees from it. So because of this, there's a lot more uncertainty in the surface connectivity. So it's kind of bouncing back and forth between two polar coronal holes. So that's why you see this frequent color change in polarity, indicating polarity. And during the co-rotation period, Parker's embedded with a negative polarity field that ranges from 0 to 12 degrees of separation from the heliospheric current sheet. And then as Parker comes out of co-rotation, the spacecraft crosses the heliospheric current sheet and becomes up to 20 degrees separated. So this is a plot comparing the model-derived IMF and solar wind speed in blue for our best realization and the Parker observations in black. So you can see here, this is where the model was skimming the heliospheric current sheet. So that's why the polarity is slipping back and forth. We're also about a day off in this heliospheric current sheet crossing prediction, and this is partially due to a CME eruption that occurred during this time. And also for a large portion of this encounter, Parker is on the far side of the sun, so overall we obtained pretty good agreement between the IMF and solar wind speed. And this is in large part due to there not being any substantial new active region emergence during this time. So we're actually pretty fortunate to be able to capture this encounter so well. So this is a plot of the WSA-derived coronal holes that best summarizes the time period surrounding perihelion. So for nearly all of the co-rotation period, Parker's connected to this mid-latitude coronal hole that extends from the south. This is a still, so it represents the coronal hole as it appeared on November 5th. But if we look back to October 29th, we can see what this coronal hole looked like when Parker first began to observe it. And it's much different, as you can see in the black circle. So I'm actually going to play a movie where it's going to show 10 or so days where Parker's observing this coronal hole, and it's connected to it over the entire time. So you can see this coronal hole increase in surface area from the 1st to the 8th, and then it starts to close down, shrinking significantly. So Parker was observing this coronal hole as it evolved in time, and this had never really been done before. So after co-rotation, Parker crosses the heliospheric current sheet and connects to another mid-latitude coronal hole, which is indicated by these arrows. So these two coronal holes form a small helmet streamer with a 3D rendering of that on the right here. So for the first encounter, Parker is either observing heliospheric current sheet wind or wind originating from this coronal hole as it evolves over 10 days. So one final remark on this encounter as a whole is that this is a plot of hourly average parameters for those field lines that are the source regions of the Parker observed solar wind. So we know from the previous coronal hole plots that Parker co-rotates with the sun for about 10 days, shown here. However, embedded within this period, there's about a 5-day period in which the expansion factor, coronal hole boundary distance, and the field strength of the photosphere remain nearly constant. So this kind of indicates that Parker's sampling the solar wind from not just the same coronal hole, but precisely the same source region within that coronal hole for these 5 days. Currently what we're working on now is really investigating how the solar wind evolved over that 5 days, and also looking at L1 observations from the same coronal hole as well. And so lastly, at the end of this solar encounter, Parker was fortuitously aligned with stereo A such that the two spacecraft could observe a coronal mass ejection. So this figure shows the location of Parker, stereo A, and Earth at the time of the eruption. The event was first observed in stereo A coronagraph data out to about 15 solar radii, and then was observed at Parker, I think about a day later, or within the same day, but almost a whole day later. So this is just a video of the event. You can watch here the events coming off on the east limb. And I'll play it again because you can almost kind of see it disconnecting from the sun. Right about there. Okay. And these are the observations for the CME. At the time, the spacecraft was at 54.7 solar radii. I was not involved in the data analysis, but I'm just showing this for context. So in between the two dashed lines here is where the event occurred. So some of the clear indicators as a CME is the increase in the magnetic field magnitude, which is right here. And it's coinciding with the rotation and the tangential and normal components of the field. You also have a plasma beta that's much less than 1. And if you look at the electron pitch angle distribution, you show electrons flowing both toward and away from the sun, indicating that those field lines are still closed. So what was intriguing about this event in C2 is that it's really slow and there's not really a clearly observed shock front. So in the data analysis process, like the co-authors were speculating that this could be like a streamer blowout, like a specific type of CME that is very slow, doesn't necessarily have to have a shock front, and it typically originates from a large helmet streamer in quiet sun magnetic field. So I was tasked with deriving the source region of this event to determine if we could see if it was, in fact, if we can like help confirm that it was a streamer blowout CME. So since WSA is a magnetostatic model, it's not the type of model that can simulate these kinds of eruptions. But because there was the remote observations from stereo A, we can actually look at when this event was first observed in the low corona and then derive the coronal field for just that specific time period. So if it wasn't for those remote observations, we wouldn't have been able to do this kind of study. But we used the average speed of the event and assumed radial propagation. And then we're able to like narrow down the source region of this event in that way. So the blue oval here is where Parker was co-rotating with the sun. But however, if you look at the coronagraph data, the first evidence of this eruption was November 10th at about 2 a.m. So that's the green oval here. And this is actually the helmet streamer that Parker Solar Probe would have observed the event from. So you can look at this here. This is a 3D rendering of that same helmet streamer. Structure is quite large. It spans about 900 megameters at the photosphere. The magnetic field strength is at the surface is only about 10 Gauss. It's exactly the type of helmet streamer that would form a streamer blowout. They're typically, streamer blowouts typically form between a polar coronal hole and they have quiet sun magnetic field. And so with our modeling work and all the data analysis, it really was neat how the narrative all, it's all told the same narrative. We were able to really characterize this CME quite well. So just in conclusion for the Parker work, basically ADAPT-WSA is fully updated and capable of deriving the Parker observed solar wind, as well as now Solar Orbiter. I've worked personally most extensively with the first 2 encounters. However, in the interest of time, I did not discuss the second encounter with you guys today. So the modeling thus far, or the modeling results initially were used in, I was involved in 4 of the different publications for the first results papers, but I think WSA as a whole was about 7 of those papers. So, and then from there, there's been several others as well. So they've been used in those 4 papers. We used the model solutions to derive the sources of small SEP events, this CME. We also did a study with Adam Szabo to compare all the model, like MHD and all the different types of models basically, and what they were deriving for the first perihelion. So yeah, and then in both encounters, the solar wind emerges from coronal hole boundaries, from field lines that form helmet streamers at the heliospheric current sheet. So what I'm most interested in is holding out for Parker to observe deep inside coronal hole wind, and then from there really being able to look at the differences and characterize the wind from the boundary versus deep inside a coronal hole. So currently, like whatever hasn't been published already from like different co-author papers I've been on is in prep for publication, but I'm just working on a deeper analysis of that 5-day period I was talking about where Parker samples the solar wind from that mid-latitude coronal hole. So just final remarks as a whole. I basically, we talked about the ADAPT-WSA model, and I developed a methodology to derive the source regions of the observed solar wind. A modeling technique is really required to know where the solar wind came from when you're talking about source region in this way, in terms of this framework on the left here. And so our results can be well described within this framework as well. So one of the things I'm now working on that's sort of been like my postdoc proposal was that to investigate both pseudostreamers and helmet streamers and determine whether solar wind properties are more dependent on the local magnetic topology at the source, such as active region or quiet sun, or the larger magnetic structure, such as pseudostreamer or helmet streamer. And yep, and that's it. So thank you so much.
Thank you. Very nice. Does anyone have any questions? If you do, we have a raise hand feature, or feel free to type something in the chat.
Should I exit out so I can see the chat?
If you like, but I can monitor that as well.
Okay.
Don't worry. So I had a question about the first part of your work when you were trying to find correlations between the solar wind speed and the expansion factor.
Yeah.
So if I understood correctly, the only real correlation that you found with any real significance there was the speed with distance from the coronal hole boundary. Is that right?
Yeah, so we found a moderate correlation when comparing solar wind speed and the distance that the source region was from the coronal hole boundary.
Okay, so then my question is, what does that mean? What does your distance to the coronal hole boundary mean? Did you find faster wind that was inside the coronal hole as the source region but far from the boundary, or is it outside the coronal hole but further from the boundary?
Yeah, I can try and go back to that slide. Sorry, it's far away. Basically, when we were closer to the boundary, we only really saw the slowest wind. Close to it. Here we go. So closer to the boundary, we only observed the slowest wind speeds. And then as we got deeper inside the coronal hole, yeah, okay, which is what this parameter quantifies, we saw a larger range of speeds. And so this plot is in some ways incomplete because we weren't really looking for field lines that are deep inside a coronal hole. So all we're really looking at is really close to the boundary, and then you're really just, when you like have this numbers between like 2 and 3, you're just starting to get deeper inside the coronal hole. So what we're wondering and speculating is, would we only see faster wind once we're deep inside the coronal hole? So would this correlation be stronger, basically, if we had more?
Does this also imply then that larger coronal holes should have larger speeds because the center of them is going to be even further from the boundary?
Yeah, it could imply that, yeah.
Is that something that we've seen observationally? I'm not really up to date on that.
Yeah, I mean, that's something that's like how typical of the solar wind is when you're deep inside a coronal hole. That's where the fast solar wind comes from. But this in particular, it's like kind of splitting hairs because we're just looking at creeping into the coronal hole versus being really confident we're deep inside. But as with any study, there are several caveats. Like in this study in particular, in terms of expansion factor, there are other studies that suggest that instead of looking at the original definition of expansion factor, we should take the maximum value of the expansion factor along pseudostreamer field lines, because there are, like, along that field line, they do expand. There is a lot of expansion. It's just that once you get to 2.5 solar radii, it's typically converging and nearly radial again. So, so it's possible that it's just the way we're quantifying expansion factor that is part of the problem, and there may be better ways to do that. So.
Okay, thank you.
Yeah.
You have a question, Sarah?
I think you may have actually just answered it. Because I was going to ask, yeah, so you were talking about how you wouldn't expect the correlation because of the proximity to the boundary, and it's a more dynamic area, for example. But the other possibility is if there's a refocusing of the expansion factor, right? And especially if there's a magnetic null, below the area where you're doing your expansion factor, you could have it kind of coming in and so it's expanding and then refocusing.
Right.
And so do you know, and so with the Wang-Shili RG PFSS and is there a way that you could take that into consideration, and how would you do it?
Yes.
Expansion factor versus height.
So that's something that we've talked about. So basically what we could do is replace expansion factor like as traditionally defined by Wang and Shili with the maximum value. So just for everywhere along the field line, whatever the maximum value of the expansion factor was, that would be the new quantity. So the hard part with that is that it hasn't been fully tested for other scenarios besides pseudostreamers. So it's been shown to kind of recover this relationship for pseudostreamers, but does it still work if there's a helmet streamer? Does it still work if, all these other scenarios of the different magnetic topologies? So we'd have to really test that before changing how we define that quantity. But I guess as a reassurance in some ways, the way we calculate solar wind, it's really far away. I'm going to stay here. So the solar wind speed equation, it's actually more weighted on the coronal hole boundary distance anyways. So typically, basically for the amount of time that overall that we would observe pseudostreamer wind versus helmet stream and all the other things, the coronal hole boundary distance is going to be more the driving factor in the solar wind speed equation. So in some ways these things work itself out, but yes, it would need to be investigated for sure. And that's another thing I just want to bring up too, is that it's so hard to present this study because I'm not saying that expansion factor is doesn't work at all. It's just we were looking specifically at pseudostreamers. So yeah, and from what I haven't done this thorough of a study for helmet streamers, but from what I've just seen from the few I've identified, it does hold up very well for helmet streamers. So.
Okay, we have a question from Phil Judge. Do you want to ask that, Phil, or should I just read your chat? I guess I'll just read it. Okay, so his question is, what measurements of magnetic field near the coronal base would help in understanding these issues? And I guess by these issues, he means determining the magnetic field further out into the solar wind.
Well, one thing is that, we typically talk about these models in missing not having the far side observations of the photosphere, but really that's only one side of the problem. That is the lower boundary condition. So another thing that we really don't have at all is the upper boundary condition, which is the coronal magnetic field. So those observations would have to be really critical to having an upper boundary condition. So not only do we really need whole sun observations of the photospheric magnetic field, having whole sun observations of the coronal magnetic field would be really critical to not just potential field models, but all modelers, and really, and I think that's one of the, I think the models, not necessarily WSA, but the MHD codes are super robust, and really the progress at this point is inhibited by just the need for those observations. It's not that the codes aren't good enough or computationally efficient, or sure, those things could always improve, but really having those boundary condition observations are going to be what advances our understanding over the next 10 years, 20 years, whatever. So.
Go ahead, Sarah. She had something to follow up.
Yeah, I can't resist commenting. Yeah, I completely agree, and I think there's the comp observations of pseudostreamers, which where we've compared them to potential extrapolations and showed where for example, the magnetic null height and the expansion is that comp shows in the linear polarization is different than potential field. Would you be able, if you had observations like that, would you be able to use them to guide or calibrate studies like this to know when the potential field model is not necessarily capturing the expansion of field correctly and thus not getting the expansion factor correct? How would you use that if you had that information?
I think it would be possible. I don't think I would be able to. I think it's difficult because I tried to do a study where I was looking at all the different pseudostreamers identified in C2 and then trying to kind of find them in remote observations. But what I quickly realized was that not all of my pseudostreamers, so to say, like in this study, are going to be observed on the solar limb. So it was difficult because like not all of them are pseudostreamers formed in longitude. Some are formed over a span of latitude and vice versa, or whatever. So I think if we were to do something like that, it would be just a few cases of pseudostreamers. And I'm not super familiar with the comp observations and how I would incorporate that, but I definitely think there is something there that could be done that would definitely help validate the model determination of expansion factor.
So on that point, kind of my impression of the way that ADAPT-WSA and these sorts of kind of solar wind modeling codes work is they kind of rely on synoptic full sun data as much as possible, right? So if you had coronal field measurements that were not full sun and it was only like small subset, is that useful in any way to these models? Is there a way to incorporate that? Or do they really need something more synoptic?
My first instinct would be to say more synoptic, but it doesn't mean that those observations wouldn't be useful for other models that are, I think it's possible to use them. I just have to look at, you know, just one portion of the model solution in my case versus the whole sun, which could be difficult. But I think that there's a mission at Goddard that is going to be on the ISS, and it's called Codex, and they're supposed to have, I think, velocity, temperature, and density measurements. I think magnetic field, I'm not sure, of the corona. So like something like that, where it's more like whole sun, or at least, you know, half sun in that case, would probably be more useful for this type of modeling.
Okay, thank you. And any more questions? I saw you put your video on, Ian. Did you want to just show your face, or do you want to ask something?
No, I was just trying to show her that she's got interest and support out here.
I have what?
Oh, very interesting presentation. I appreciated it, and I thought it would be nice for you to be able to see some people's faces.
Oh, well, I can't. Let me stop sharing so I can actually see people's faces.
Oh, well.
Okay.
Okay, in that case, thank you very much again. And,
yeah, thank you. Hopefully I can come visit sometime in person.